this video, I want to talk about damped free vibration, which is damping due to some viscous effect on the oscillating motion. So viscosity or the viscous damping effect is usually thought of as a resistance to the motion due to moving through some fluid such as water or oil or air, which would all be common methods of damping. However, in reality, pretty much all vibrations are damped. And this is the reason that they eventually die out, in that we don't expect a vibration to continue on forever because there's energy losses due to all sorts of inefficiencies of material deformation and air resistance and things like that. So we're going to talk a little bit about this viscous damping effect and how we take it into account for free vibration. So if we were to think about a mass which is attached to some fixed plane using a spring like we had before in undamped free vibration, but now we're going to add to that a dash pot, and the dash pot is the usual symbol used to model viscous damping. So again, we have a mass that can be displaced by some position x, being counteracted, that motion being counteracted by the spring and by the dash pot. So if we take this in a free body diagram form, we would have the weight, and then we would have forces, one due to the spring and one due to the dash pot. And this is our classic mass spring damper system that you may hear of if you take anything in vibrations or talk about vibrations through a more in-depth course. So the new part here is this force due to the dash pot. And the force, we're going to say, is equal to Cx dot, where C is our damping coefficient. Now, one thing we should notice here is that the force of the dash pot is proportional to the speed, represented by x dot. So that's the velocity of the motion, rather than where the spring force is proportional to the x displacement itself. Velocity from the force from the dash pot is proportional to the velocity. So with higher velocity, you're going to get greater resistance from the dash pot. If we move slowly, we wouldn't expect very much resistance. So this damping coefficient is what controls that and kind of defines the damper and how it influences the system. The units on the damping coefficient are Newton seconds per meter or pound seconds per foot as a couple of options. So we've got a model for this mass spring damper system, and once again I'm going to take a summation of forces, and this is probably not in the y direction since I've labeled it x, but we'll just say a summation of forces of W minus Fs minus Fd equals mass times acceleration. Recall from our analysis before that the weight is equal to k delta, so that relates our spring and our weight, and therefore we can write this equation as minus kx minus cx dot equal to mx double dot. So again, this W term drops out because we're considering only the initial deflection beyond the equilibrium position, and those terms that include k delta drop out of our equation. So if we rearrange this equation, then we can write it of the form mx double dot plus cx dot plus kx equals 0. So it looks a lot like our standard form equation for our undamped free vibration, but we've added in this new term Cx dot, that wasn't in that equation before. So the next process is to find a solution to this differential equation. So the equation we have here is a linear second-order homogeneous differential equation. And you may not have taken a differential equations course prior to taking a course in dynamics, so we're not going to worry too much about how to arrive at a solution to this equation, but we will say that there is a general form solution which looks like x equals e to the lambda t, lambda being the commonly used variable to represent the constant that defines the solution to this equation. Now e is just the exponential function, and therefore we have this equation for x. Now I'm going to go ahead and take that and substitute it back into my initial equation here. So the second derivative of x, if x is of that form, would look like this. The first derivative like this. And we get an equation that looks like that. Now there's a common term in here, which is e to the lambda t, so I can pull all of that out. And I could then divide this across into the 0, and I'm left with m lambda squared plus c lambda plus k equals 0. Now, ultimately, we're looking to solve for lambda so that we can specify what x is, and x requires lambda in order to be usable. Now, if we look at this equation, we have a relatively standard form second order equation, and therefore we can use the quadratic formula to find the roots. And if I do that, if I make use of the quadratic formula, I get an equation, two solutions that look like this. So this solution set, lambda 1 and lambda 2, represents the two possible solutions to that second order equation in terms of lambda. Now the key here that we'll need to think about is what the influence is of this portion of the equation under the square root. So the square root poses potential problems in that if the terms under the square root are negative, then that yields an imaginary result. If they're positive, it yields a real result. And somewhere in between, we get the transition point between those two things. So in the next video, we'll talk about how we look at that and what the potential solutions to lambda 1 and lambda 2 cause in terms of influence on our resulting output. So I'll stop there. Thanks.